Welcome back to the video series of my course on solid state devices. This video will discuss the elementary concepts related to elemental and compound semiconductors and corresponding fundamentals. This would be rather a look back on certain topics that you might have studied during 10 plus 2 physics. We discuss about semiconductors because in our day-to-day life we are benefiting by the devices which uses semiconductors. Before we understand what semiconductor is, let's look on the other types of elements that we have. One type of element is called as conductors. Conductors are those which conducts electricity freely. So there is another group of elements which will not conduct electricity at all. Those elements are called insulators. Semiconductors falls in between conductors and insulators. That means their conductivity can be controlled. This property of semiconductor whose conductivity can be controlled enables it to be used as many devices. It can act as switch, it can act as amplifier, it can also act as LED, light emitting diode, solar cells. In all the electronic devices, the basic element is the semiconductor device. From the television that we watch till the electric vehicle which are going to rule the roads have this basic component made up of semiconductors. How these elements are showing this variation in conductivity can be explained using the energy band diagrams. For energy band, there are three major constituents. One is the valence band. The valence band is the band of electron orbitals that electrons can jump out of, moving into the conduction band when excited. The valence band is actually the outermost electron orbit of an atom with electrons occupying it. Another constituent is the conduction band. Conduction band is a band where the electrons can jump from the valence band when excited. When the electrons are in this band, they can move freely. This free movement creates the electric current. Or in other words, if there are electrons in the conduction band, the element will act as a conductor. Apart from these two bands, there is a third part in the energy band, which is the band gap. It is the actual distance between the valence band and the conduction band. As you can see in the figure, in case of insulators, this gap is very big when compared to that of semiconductor and conductors. In conductors, we cannot even see a band gap. That makes the conductors easily conducting the electrons. The electrons in the valence band can easily move on to the conduction band, which makes it conductors. But in case of insulators, since the band gap is big, electrons from valence band should gain more energy to escape from valence band and reach the conduction band. That makes its conductivity minimum or zero. That is why it is acting as insulators or non-conductors. In case of semiconductor, the band gap is in between say 0.67 to say 2 electron volts, which is less when compared to that of insulators. So it is easier to excite electrons from the valence band of semiconductors to conductors. This property of semiconductor, where we could control the number of electrons in the conduction band by exciting the electrons from valence band, helps us to use these semiconductors in semiconductor devices. Now, how these energy bands are being made, or how it come into existence, is a question. Let us see how the energy bands are formed by seeing an example. Let us take the example of isolated carbon atoms forming diamond crystals. If we look into the isolated carbon atom, it has an electronic structure 1s2, 2s2 and 2p2 in the ground state. Each atom has available 2 1s states, 2 2s states and 6 2p states respectively, which means that there will be 2 states in the s orbit for the electrons to occupy. Now, if we consider n atoms, we have 2n, 2n and 6n states of 1s, 2s and 2p states respectively. Now, this is the case of individual atoms. In order to make diamond crystals, we bring these atoms closer. As the atomic separations are reduced, the atoms of 2s and 2p states merge. The atomic separation of atoms 2s and 2p states merge to give 8 n states. As you already know, we had 2n states in case of 2s and 6n states in case of 2p. So on merger we will be having 8n states. Further decreasing of the atomic separation, or as the distance between the atoms approach the equilibrium interatomic spacing of diamond, it split into 2 bands. Bands namely the conduction band and valence band. Now the 8 bands formed by the merger of 2s and 2p states will be split into 2 bands with 4n states each. And these 2 bands will be separated by a gap Eg, which is the energy band gap. We should see the picture from right to left. So initially we had 2p and 2s orbits with 6n states and 2n states respectively. On bringing the atoms closer, that is, by reducing the atomic separation, they merge to give atom states, which is in the middle portion of the figure. Further reducing the atomic separation until it reaches the equilibrium interatomic spacing, it will split into two bands with 4n states each, and each band is separated by a gap, also known as the forbidden gap, which is the energy band gap. This can be used to analyze the energy band of non-semiconductors, which are silicon and germanium. In case of silicon and germanium, the outer orbit has 4 electrons, which will fill the 4 states in the valence band. So the valence band will be full with the electrons. We are having only 4 states in the valence band, and we are having 4 electrons. Thus, the electrons are immobile because there are no free states in valence band for the electrons to move. The electrons can move only if it is excited to the conduction band. As in the band gap diagram, we know that as we are having 4 states in the valence band, we are also having 4 states in the conduction band. So only when the electrons are excited from the valence band to the conduction band, electrons have free states to move. So once the electrons are excited to the conduction band, it is free to move. But in order to reach the conduction band, the electrons have to cross the band gap, which is, in case of silicon, it is 1.1 electron volt, and in case of germanium, it is 0.67 electron volt. This scenario can be kept in mind to analyze what happens to a normal semiconductor element in room temperature. As you all know, we will take the example of silicon. The energy band gap of silicon is 1.1 electron volt. 1 electron volt is actually equals to 1.6 into 10 raised to minus 19 joules, which is the energy of 1 electron volt in terms of joules. Every atom in room temperature or any temperature will have a thermal energy, and due to this thermal energy, it will be vibrating. By equation, thermal energy is equal to kT, where K is the Boltzmann's constant, which is equal to 1.38 into 10 raised to minus 23 joules per Kelvin. And capital T is the temperature in degree Kelvin. As you all know, room temperature in Kelvin is around 300 degree Kelvin. So what will be the thermal energy at room temperature? Which is equal to K, the Boltzmann constant, 1.38 into 10 raised to minus 23 into 300, which is the room temperature in Kelvin. That will be giving thermal energy in joules. In order to convert it to electron volt, we need to divide by 1.6 into 10 raised to minus 19, which gives us the thermal energy at room temperature as 0.026 electron volt. Now this energy is far less than the energy required to jump for an electron to jump from valence band to conduction band. In case of silicon, since the energy band gap is 1.1 electron volt, the electrons will not get excited from valence band to conduction band in room temperature. So if we are using pure semiconductors, we need to increase the temperature in order to have electrons excited and moving from valence band to conduction band, which is not possible normally. Our devices that we use are working in room temperature. So we need to find an alternative for having electrons in conduction band. That we will see how it is being done in a later part of this video. Now let us have a throwback on certain things that we already know. It's like a gentle reminder. In a semiconductor, the current carriers are electrons and holes. Unlikely in conductors, the current is due to the movement of electrons, but in case of semiconductors, there are two carriers which are electrons and holes. Electrons have a negative charge and holes have a positive charge. Holes can be sometimes confusing as they are not physical particles. The absence of electrons are known as holes. That is the basic thing that you should remember. Another basic concept is that of doping. We had seen by the example of thermal energy that pure form of semiconductors can conduct only when it is excited by temperature. Practically usable semiconductors cannot be pure form. So addition of impurity will change the conductor ability of a semiconductor. And this process of adding impurities to an pure semiconductor, which is called as the intrinsic semiconductor, this process is called doping. And the impurity that we add is called the dopant. So now we know there are two general category of semiconductors. One is the intrinsic semiconductor and the other one is extrinsic semiconductor. An intrinsic semiconductor is a pure undoped semiconductor, which means that the elements are in its pure form. Electrons have to be thermally excited to reach the conduction band. Silicon and germanium in its pure form are the best examples for intrinsic semiconductors. Whereas extrinsic semiconductors are made by doping impurities to the pure or the intrinsic semiconductor. In other words, after doping, an intrinsic material becomes an extrinsic material. There are many types of impurities, or rather two types of impurities. One is a pentavalent impurity. Example, arsenic and antimony. Or another type is trivalent impurity. Examples are indium and gallium. Addition of pentavalent impurity gives N-type semiconductors, and addition of trivalent impurities give p-type semiconductor. Pentavalent means there are 5 electrons in the outer orbit. So when that impurity is being added onto the semiconductor, the pure form of semiconductors or the intrinsic semiconductor, which are having only 4 electrons in its outer orbit, one electron will be left behind or left free, which can easily act as free electrons and contribute towards the conduction. Similarly, if a trivalent impurity is being added, only 3 of the electrons can form bonds with this trivalent impurity electrons. So there will be a gap or hole devoid of electron, and this hole is contributing to the conduction in p-type semiconductors. This can be made clear by this diagram. On the left hand side of your screen is an n-type semiconductor. You could see the n-type impurity arsenic is having 5 outer orbit electrons. 4 of them will bond with the silicon atom, leaving behind 1 electron as free electron, which contribute to the conduction. Now, in the right side of the screen, you see the p-type semiconductor, where the trivalent impurity indium is being added. You could see only 3 of the silicon atom can form bond with this indium. The 4th electron is not having another electron to form bond, and that forms the hole. So this gives us the basic idea of what an extrinsic semiconductor is. There are 2 types of extrinsic semiconductors, which are n-type and p-type. Both are extrinsic semiconductors. With this, we will stop discussion on this elementary topic regarding semiconductors. Let's see what are in store for us in the coming videos. This is a pointer to the next sessions. We will see some more fundamental ideas of energy band through understanding effective mass, the concept of effective mass. We know the free electron is having a mass which is 9.1 into 10 raised to minus 31 kilogram. Is denoted by M0. But in a crystal, though we call it as free electron, it is not completely free. So there is a concept called effective mass, M star, which is not equal to M0. We will see this in detail in our next video. And in coming sessions, we will be discussing about Fermi-Dirac distribution, state conditions, concentration of electrons and holes, so on. I hope you have a clear idea of some of the basic fundamentals of semiconductors through this video lecture. Thank you.